All right, so Chris is going to be presenting a talk on efficient boundary value problems solving in SciML. So let's welcome Chris.
Yeah, thank you very much. I'm presenting, but this work on the boundary value problem solvers, I think that this one has spanned since 2016, actually. For those who know, Yingbo actually started working in SciML as a high school student, and his project that he started working on was the boundary value problem solvers. And now we're hitting 2025, and I think we finally have enough tooling to be able to tell people that we have good boundary value problem solvers, right? And so I want to be able to show people like how cool this algorithm is, because this is probably the one that we spent the most time like putting cool stuff all together in. I'm taking this from Qingyu. This is the student who has been really kind of driving these efforts. So he's supposed to give the talk today, but he couldn't make it here. And also Avik Paul, who's you might know him from Lux.jl and stuff as well. He's also done a lot within the boundary value problem stuff. He's here, and you'll see why, because there's some really cool automatic differentiation in here. So let's dig into it. Why are boundary value problems? Why is this then the topic of our SciML 2025, right? So let's. So what's the background here? Well, the main background is for a long time we focused a lot on initial value problems, and so if you look at the old blog post that we had back in 2016, I think we kept on updating it to like 2019 or so. Kind of said, oh, here's where we do well, here's where we don't, and one of the places we highlighted is like we're all right, but it's not great. Is boundary value problem solvers, right? One of the other ones was differential algebraic equations. I think we've smacked that down over the last 5 years or so. But boundary value problem solvers was the one where it's just like, okay, we don't really have all the stuff that every ecosystem has, right? With the ODE solvers, we're like, okay, every single other ODE solver, we have a bit-for-bit recreation of it, and then also additions, and we went overboard there. But boundary value problem solvers, we didn't really have much for quite a while. We had some shooting methods, and the shooting methods had some good properties, but boundary value problems weren't our stronghold. Well, what I'm here to tell you today is that we've went overkill on this. So when we talk about boundary value problems, what kind of problems are we looking at? We're looking at the regular boundary value problem. So this is actually something that covers multi-point boundary value problems, right? So it's an ODE where you can put constraints, or the number of constraints. You'll see that the number of constraints, in theory, should be the number of the number of equations that you have. Though it turns out that after you do the numerics with a bunch of additions, you can make there be as many constraints as you want. Also, they don't. If it's a normal boundary value problem, you can put those constraints anywhere. So you can say something like the maximum of my equation is 5, and it should happen at t equals 5. That's 2 constraints. Boom. That's a boundary value problem. It's probably not the boundary value problem that you've heard of before, right? But usually when we think about a boundary value problem, it's what's the value at the start, what's the value at the end, right? And boom, or what's the value at the end is so that's what you normally call a 2-point boundary value problem. We do have a 2-point boundary value problem constructor, and then we have second order versions of these as well. And I'll show you exactly why in a second, why most software focuses on 2-point boundary value problems and why we no longer care, because that really comes down to tricks with automatic differentiation. So, so what are some good examples of boundary value problems? Well, there are these 2-point BVPs, which a lot of people have written down. So like the swirling flow problem, you find them in satellite motion and all sorts of different cases. You also find boundary value differential algebraic equations, like hydraulic models that tend to have this. But also, one of the things I'll be showing is that things like optimal control problems actually can be represented as a multi-point boundary value problem. And if you just call the boundary value problem solver, it gives you out the optimal control as part of its solution process. I'll show you exactly how that's done, and this is why this boundary value problem solver, we might even rename it to be dynamic optimization.jl, because it does these things that we really wouldn't consider boundary value problems anymore. But this is all about the next steps, right? So what kinds of boundary value problems can we handle? So this is a I thought I had the 30-minute talk though. Yeah. Yeah, so what kind of boundary problems can we handle, right? So you can basically split it into two portions, right? One portion are your non-stiff boundary value problems and your stiff boundary value problems. And in the non-stiff section, you have all of your shooting methods, right? And you might go, okay, so first of all, what is a shooting method? And I'll tell you in a second. I mean, basically, you're using an ODE solver as part of the boundary value problem solver. And you go, well, what if if you have stiff ODE solvers, can you use a stiff ODE solver with your shooting method and end up with some? No. It turns out that there are limitations to the stability that you can have when solving these problems, even if you're using an initial value problem solver that is capable of handling stiff equations. And so shooting methods are naturally in this form, for these types of problems, it naturally is less stable than doing other techniques, right? So shooting methods kind of fall into this. If your boundary value problem is easy enough, then you can do some form of shooting. If it's less easy, you can still get away with multiple shooting. If it falls into the hard category, no shooting technique is going to work, right? But then there's also these other techniques like Merck techniques and Merck-N techniques. Merck-N are Nystrom Merck methods, which are non-stiff tableaus that are specialized to boundary value problems. And then we have this whole group of methods that are specific to if you have a very highly stiff boundary value problem and you want to solve that to high accuracy, then there's Lobato tableaus, Asher methods, and Radow tableaus, right? So let me give a little bit of a background on a few of them, right? So what's a shooting technique? Well, the shooting technique, so let's say you have a 2-point boundary value problem, right? So you're given an ODE, and you're given what the value of the solution is at the end. You don't know what the beginning is. Well, maybe I should switch this to the audience that is expecting things to go from left to right, right? Here is the beginning, here is the end, right? You have an ODE that tells you go from here to here, but you know the solution at the end, right? So what you need to find as part of the boundary value problem, the solution is to find the initial condition that makes you get to the right endpoint, right? So it's basically an inverse problem. Find for me the initial condition such that when you solve the ODE, you hit this endpoint. So you can think about it as, well, if I have a way to solve ODEs, I can just use that, right? I pick an initial condition, I solve it, oh, I missed. I'm going to maybe move my initial condition down a little bit, I missed. And boom, oh, this is the right initial condition, right? So that's what a shooting technique is doing, right? It's using the ODE solver and differentiating the ODE solver to basically just find what initial condition will give you the output that satisfies the constraints, right? And this is, if you've done parameter estimation with ODEs, it's using exactly the same infrastructure that you would do for parameter estimation and all those bits, right? Which is why it was one of these pieces that just kind of existed for boundary value problem solvers in SciML because, oh, we worked so much on the initial value problem differentiation stuff, let's just repurpose this for boundary value problems. And it turns out that this is extremely fast as well. In fact, if shooting works, it is by far the fastest way to solve these boundary value problems, right? And you can see that multiple shooting is this kind of technique where you say, instead of going from the start, you go like, a quarter of the way, and then you have a different solve, go a quarter of the way, and you just split up the interval. It turns out that if you split up the interval, and then you say, oh, there are two constraints. One constraint is that you have to hit the endpoint. The other constraint is that the differences between where you start in the next interval and where you end needs to go to 0. Then you're searching for not just one initial condition, but now the initial condition of every interval. And once you find all those, you have a nice smooth trajectory that goes from start to finish, right? Now I flipped it in the other direction, but we're good, right? So this is the shooting method, right? And it kind of came for free with everything else we did. But as I mentioned, if you get to a stiff enough boundary value problem, these will not be able to fit because the fitting process ends up being unstable. And you can prove that even if you have a stiff ODE solver, this ends up being unstable. And that makes us sad, right? So what do we do? Well, what we do is we say, oh, that's what we have for the first 5 years, and then we say, oh, let's come up with an algorithm that's extremely good. And you go, well, there's no way any ecosystem has the tools to do this until now, right? So what is the algorithm that we're going to do? Well, it's actually built off the algorithms you might have heard before. These are collocation methods, right? So what you do with a collocation method is you write out your method so that way it's you take a time step. So let's say we have like Euler's method, right? So we have a time step here, time step here, time step here, time step here, time step here. You write out every single time step. And what you're searching for is what is the value at this time step, this time step, this time step, this time step, all all of them, such that your ODE equation, right, your discretization equation is satisfied, right? So you know the Euler method is un, un plus 1 equals u sub n plus delta t times f of u sub n, right? You know, you have your simple take the derivative step forward, right? What you want to do is you want to find the values along the entire time series such that the Euler equation is satisfied at every single step and that your boundary condition is satisfied. If you write this out as a gigantic system, you end up with a system where you're searching for what is the value at every single time point. You're searching for what's the value at every single time point. For every time point, you have is my derivative the correct value right at each time point, and you have your conditions. Basically, it just becomes a big optimization problem where you just say solve for what all the values at all time points are simultaneously. So that's a co-location method, right? And you might have even done this if you've used an optimizer before, right? Some people will say use will use jump, or you'll use Pyomo or one of these tools. You'll just write out a fixed time discretization, and then you just say, okay, for this to actually be solving this ODE, then the discretization has to be true at every time point. Run an optimizer and find all the time points, right? So there really isn't nothing new about co-location methods. People do this. So what can we do with these co-location methods that is, making it so that we're evolving in this space, right? So the key here is to do a version of automatic differentiation and specialize the linear algebra, so that way you're doing a mixed mode. So part of it's doing forward mode automatic differentiation, and part of it's doing reverse mode automatic differentiation with sparsity detection in order to do this adaptivity. So let me explain this a little bit, right? So when you do the co-location method, right, you have all of these different points where you say, okay, un plus 1 equals un, you have an equation for what the update step is supposed to be. And you have that equation at every single point in time, right? And in fact, u of 1 is related to u of 2. U of 2 is related to u of 3. U of 3 is related to u of 4 through this time-stepping equation, right? And based off of the tableau that you're choosing, you'll have some kind of banded pattern, right? Because you say, oh, u of 2 is related to u of 1 and u of 3, right? Through the two different equations. And u of 3 is related to u of 2 and u of 4 because of how they're... And so that banded pattern is actually what you're seeing here. So from the equations that you have for the co-location part, you have a banded matrix. But then you also have your constraint equations, right? And from your constraint equations, you have something that can, in theory, depend on any point in time, right? So what happens is, if something like MATLAB or some of the old Fortran software say, well, this is kind of difficult because if in theory, if the constraint equation can depend on any possible value in the time series, then I have a few dense rows in this matrix for the Jacobian. But if I have a 2-point boundary value problem, then my constraints can only depend on the values at the front and in the back. And if that's true, then this density, then everything in the middle here is gone, and I just have some non-sparsity here and here, and I get a banded matrix. Right, so something like BVP4C, BVP5C, Lawrence Champine noticed this and said, you know what, we will support 2-point boundary value problems inside of MATLAB because you have the structure, and therefore everything's a banded matrix, and therefore we can specialize how we compute the derivative, and we can specialize how we do the linear algebra, right? Great, that's how they did it, but can we do something better, right? So what we can do now, though, is we can say, well, we have the constraint equations, and we have a tool. This tool is called automatic sparsity detection, right? With automatic sparsity detection, we can actually look at the function, and we can say, do you ever use this value? If we look at a compiler level, we can figure out what pieces of the function you actually use inside of your equation and pull that out to know what the sparsity pattern is. So instead of assuming that this is a dense row, we can actually figure out what that sparsity pattern is. And if it is something that is, then there's two things to do here, right? First of all, if you have a banded matrix, it turns out that you can specialize forward mode automatic differentiation. So if you know things about forward diff and the chunk size, you can choose the chunk size of forward diff such that it is equal to the band size of the matrix and compute the entire banded matrix here all in one pass through your function. So you build one dual number and then you pass it on through. This is an analytical solution to the coloring problem. See some of my previous we'll see some of my lectures in the SciML book about how that analytical solution is done, right? But then this other piece is a row matrix, right? And so while forward mode automatic differentiation is best for doing columns of a Jacobian, reverse mode AD is best for doing rows of a matrix. So it turns out with all that together, the optimal thing to do to be able to compute the Jacobians for the collocation method is do forward mode automatic differentiation with the band size that is determined by the tableau of your method to be able to get all of these terms in blue, and then do passes of reverse mode automatic differentiation to compute these parts of the banded matrix at the top. And that mixture of automatic differentiation collapses and will automatically become Champigne's 2-point boundary value problem solution if you actually can discover that the sparsity pattern is banded. So boom. We get that special case for free, but then we also have a very efficient solution for any possible constraints that you write down. And so therefore, we no longer care about it being 2-point boundary value problem. Give me whatever constraints you want, and I can handle this efficiently as long as I could do this double automatic differentiation plus sparsity detection. And this is why this algorithm took so long to write. Right? We needed to completely build out everything in the Julia automatic differentiation ecosystem just to make this work. But once you have that, it's a really good algorithm. And then there's I think there's a few other details of the solver process, but that might be, So, and then what we do is then we say, okay, now and so one of the other things that we did here as well, right, is that the matrix that you get out always has this kind of sparsity pattern where you have a bandedness and you have this non-bandedness. It turns out that using sparse matrix solvers from BLOS ends up being pretty slow for this case. And so we have a library which is almost banded matrices.jl, which is a specialized implementation just for these matrix types. That is, I think it was like 4 to 5 times faster than using sweet sparse for these matrices. So so it's a specialized sparse automatic differentiation plus our own linear algebra, and ta-da, that's all you need. That's all you need, right? And so now we got some, and then not only that, but so the reason why Avik was involved in this project is that the first part of this project as well is just to make nonlinear solvers faster for these kind of matrices as well. So nonlinearsolve.jl then specializes the internal linear algebra and all the automatic differentiation of the Newton method that's used in the solving process based off of all these properties that I just mentioned, right? You piece all that together, and this is BoundaryValueDiffEq.jl's collocation methods. Oh, except for one extra thing, we also have adaptivity in the stepping. So after you do one step, it's able to figure out what the error is, the truncation error of the different steps. It will then change all the step sizes and then be able to redo, because you then have a new sparsity pattern to this Jacobian. It will refine the new sparsity pattern based off of the sparsity detection and be able to respecialize the automatic differentiation on the fly as well. So that's all we needed. With all that together, though, then we're able to do something where we're able to say, okay, we can handle any kind of boundary constraints that you want, and we can also do boundary value differential algebraic equations as well, because that's just that when you have a differential algebraic equation in the boundary value form, that's just something about the sparsity pattern of this matrix. And so since we can handle a lot of these sparsity pattern pieces automatically, we now the DAs kind of just flow through. Now, one of the things that we also then set up is we made it so that way modeling toolkit can generate to this form as well. So you can say, hey, with my ODE system, I also have constraints, right? So your normal ODE, you just define an ODE, give it an initial value, and you let it solve. But now inside a modeling toolkit, you could say, oh, here's my ODE, and here are some constraints that I want you to satisfy. And when you generate a problem with constraints, well, what's a general form of an ODE with constraints? It's this generalized version of a boundary value problem. And so you can call BV problem on that. When you solve it, it will give you an ODE that is guaranteed to satisfy those constraints, or it'll tell you that there's no solution to the ODE that satisfies these constraints. Now, one of the interesting pieces with this, right, that I think, let me see where I am on time. So one of the interesting pieces with this, right, so now that we've turned the boundary value problem solve, okay, let me just take one step back here. So we turned the boundary value problem solve to something where we say, write out what the values would be at every single point in time, and write out all the dynamic equations, and write out all of your constraint equations, turn it into one big nonlinear solve problem, and exploit the sparsity, right? But if you turn it into a nonlinear solve problem, you need to make sure that your Jacobian is actually square, right? Or if you can start to say, well, what if the Jacobian isn't square? Well, if the Jacobian isn't square, instead of using a Newton method, you could use something like a Gauss-Newton method, right? You can solve the least squares problem. And if you solve the least squares problem, that lets you handle either as many constraints as you want or as few constraints as you want. But if you're solving the Gauss-Newton version, you really don't care about sizes of anything anymore. So what you could do is you can say, hey, look, I'm going to solve for what the values of the time points are, but I'm also just going to append, just also add to that array of things that you're finding, just add the parameters. And if you do that, you can actually do the parameter estimation of the ODE simultaneously to the solving of the ODE. And it'll fully specialize everything with the forward and reverse mode automatic differentiation and the sparsity all at the same time. And so then you get this nice doohickle, which is, you basically just say, here's my boundary value problem, and my constraint is, so you're given these constraints where you just say, u of pi is equal to 0, u of 0 to today. So this is 2 ODEs with 3 constraints, and then you want to say at the same time, fit parameters, which means simultaneously to solving this boundary value problem, also tell me the parameters that would be optimal such that these constraints are found. And ta-da! It will just give you a solution that does the parameter estimation and the boundary and the BVP solving at the same time. And again, it's fully adaptive, right? It's adapting its time steps and everything as it goes along to make sure that the truncation error and the error estimates are sufficiently small, hitting the accuracy that you need. Yeah, and so then you go, well, if you could do this with the nonlinear least squares problems, you can also take that internal part where you're doing a least squares problem and just change it to an optimization problem. And you go, yeah, you might as well. If you change it to a nonlinear optimization problem, then you can put constraints in there. Like you can say, oh, there's a maximum value, a minimum value. You can put more equality constraints and inequality constraints. And suddenly you say, okay, now I have a boundary value problem where you're allowed to give me a loss function that you want to optimize, some extra equality constraints that you want, and you also can give me some inequality constraints. And what I'll do is I'll do this exact same process, except now this is that matrix that I was talking about, the collocation matrix and everything, is now the Hessian of the optimization problem that you're solving. But if you send this over to IPOpt, boom, you can do this, and now you get the BVP that is generalized to be able to do any inequality constraints or any piece. When I said at the beginning that we really went overboard with this, I meant it. So now it's not a 2-point boundary value problem, right? It's a boundary value problem where the constraints don't have to be on the boundary, and they also don't have to be equalities, and you can have algebraic equations as well, and you can have as many or as few constraints as you want. But it's so fast. And then, as I mentioned, there's an error control adaptivity. So what it's doing is that it'll collocate everything in time, so it's choosing some time steps at the start. And what it'll do is it'll use this kind of error control they kind of know from the other tooling, where it'll solve with different methods, it'll take the difference between methods, and it'll estimate what the error is in each of these intervals. And if any interval has too high of a numerical error, it'll split the intervals, right? So then your delta t's will be moving around, it'll be splitting intervals until all of the intervals are sufficiently small. So that way it's guaranteeing that your ODE solution between every set of delta t's is below whatever tolerance you've chosen. So piecing this all together, it'll start with a collocation. It will be solving this with a Newton method or some kind of optimizer to be able to find both the solution and parameters, right? And then if this solution plus parameters is doing something where the numerical error is sufficiently large, then it readapts the time, it splits intervals and such, and continually does this process until it has found a set of delta t's such that it is solving all the constraints of the equation, inequality and equality constraints, and it is satisfying the differential equation and any other pieces that you've told it that you want it to do. So it listens really well. It's really nice. And so I think at this point it's probably the most comprehensive and robust boundary value problem solver. It's definitely the only one that I know of that uses both forward and reverse mode automatic differentiation plus sparsity detection, and has the compiler basically do everything together with it. If you saw my talk on the symbolic numeric methods for nonlinear solving, we plan to be putting that into the middle of this as well, and I'll see what kind of cool code that comes up with. Who knows? But I think that this really kind of demonstrates one of these things with Julia where no one could come up with this algorithm in Fortran because you literally couldn't do this algorithm, right? Like you need to be able to read people's code, do the sparsity detection, and so this I think is kind of like one of these like, oh, this is what the SciML organization's really been aiming for years, and we kind of piece it all together in this, and the benchmarks, so we actually, there was someone who then contacted me and said, I have a boundary value problem that's really hard to solve. It was this dehumidifier model. And they contacted me like a year ago and I said, oh, I could help you get this going. So this paper actually recently got published. And inside of this paper, you'll see a lot of benchmarks that show that, that these boundary value problems are about 50 to 100 times faster than those in SciPy and MATLAB. And now the key here, right, is again, the problem that they were solving was a 2-point boundary value problem. So it was one where they used so Champine had done these specializations and everything, and it's also a large enough problem. So it's large linear algebra is kind of in play. And so even with these factors, you say, oh, we use the same BLAs, we use the same BLAs, and they specialize some pieces in linear algebra. Even with all of that being true, this algorithm is still able to get a massive performance improvement. And so then when you go to all these special cases beyond that, of course, a lot of them don't even support those special cases. Now, there's still a lot more that we're even thinking of doing, right? So the key takeaway is, this is an algorithm that mixes together, automated sparsity detection, automated Jacobian coloring, flexible mixed mode automatic differentiation with parts being forward, parts being reverse mode. It has our own numerical linear algebra implementation, so our own BLAs for these specialized matrices, and then it has error control adaptivity and extra choices, and it also has symbolic numeric integrations, and then you can also test it against the C and Fortran methods if you want to see. But at this point, it's kind of a beatdown because, again, this is not a very much apples to apples comparison anymore because they don't get to even do automatic differentiation, and we are doing a lot, right? So what are future plans here? You might think like, oh, this project's done. No, the issue with this project is it just keeps on going. It turns out there's a lot you can do with boundary value problem solvers, and the biggest one is you can actually do GPU stuff, right? So of course, like no Fortran code is gonna, if you give someone a Fortran code and you put it in a BVP solver and it's written in Fortran, like no one has these things doing GPU because they would require that someone would give you a GPU kernel for your ODE. But we could actually compile Julia code to GPU kernel. So let's think about this, right? As we're trying to compute the collocation and the collocation Jacobian, right? We need to evaluate the dynamics function at every single point in time. But it's the same function, just evaluated on an array. So if we could just take your ODE function and without you knowing, just recompile it to your GPU and then parallelize that computation over the GPU. And we do that on the GPU, but the constraints part, right, this other part that we do reverse mode with is not really GPU parallelizable. So we would keep that part on the CPU and we do reverse mode automatic differentiation of those functions on the CPU, while on the GPU we do forward mode automatic differentiation of the collocation methods. So this is in development. We're almost there, and the benchmark is going to be great for that. And then we're also making it so that way there's certain other things you can do. So infinite horizon boundary value problem. So you can say the endpoint of my boundary value problem is a parameter as well. Just search for that parameter. Because it's able to change around its delta t, you can make that be a search as well. And also sensitivity analysis of it. So the derivative, actually, I believe this actually works right now, where if you do automatic differentiation of the boundary value problem solve, it will turn into automatic differentiation of the nonlinear solves inside of the boundary value problem solve. And nonlinearsolve.jl does support the Zygote interface, so it should all work out, but we need to make sure that we actually test this well before we start telling people to do this. But yeah, actually, so the boundary value problem stuff goes on forever, but I will say that, one of the things that really happened in Julia with me very early on was in 2016 when we first came out with the shooting methods for boundary value problem solvers. One of the first issues that someone opened up was, does your boundary value problem solver support quaternions? And then someone put a number from quaternions.jl into the BVP solver and said, oh, it works, thank you, and closed the issue. And I looked at it and go, what are people trying to do? And then 10 years later, I'm just like, whatever you guys want to do, we're here for it. So thank you very much, and this project will keep on going. Hopefully we will make it support everything everyone wants. Thank you.
All right, Thanks, Chris, for the lovely talk. Do we have any questions from the audience?
Yeah, thank you for the amazing talk. So I think you mentioned that you have to send some stuff over to IP-opt, like Hessians and Jacobians maybe. But what's not obvious to me is IP-opt like really exploiting the exact structures of the Hessians and the Jacobians in the best possible way, or is there still more meat on the bone there?
Yeah, that is a very good question. There is so much meat on this bone. So when we have nonlinear solve, right? When we're doing nonlinear solve, our own Newton methods, our own quasi-Newton methods, our own Gauss-Newton methods, we control everything, and so we can force it to do the right this mixed mode automatic differentiation and our own linear algebra, right? When we send it over to IP-opt, right? We can give IP-opt the Hessian definition, so we can do our own mixed mode automatic differentiation with sparsity detection, yada yada. That part's all fine. But then IP-opt does its own linear algebra, right? Because it has its linear algebra built in. So I've always said, like, oh, there's no reason to ever rewrite IP-opt in Julia because it's a pretty good algorithm, yada, yada, yada. But now with this project, we're like, well, if we want to inject our own linear algebra right here, we're going to just need it. So part of what we want to do with optimization.jl now is we want to create our own version of IP-opt that's pure Julia, match its performance and everything, and then we want to be able to do that to then swap in our own linear algebra as this optimization, and that should make the algorithm about 5 times faster. So yeah, right now, though, we have to stick with just that IP-opt slows down that step and uses a sparse matrix solver.
Yeah, and then one follow-up question in the same direction. So you're now working with IP-opt. Maybe it would also be interesting to look at sequential quadratic programming, particularly for the optimal control ones. I think that still might speed things up a lot more.
Yeah, I agree. This was something that I was hoping that we'd get far enough along before Theo graduated, right? So Theo was a student that did a lot of this, quadratic programming and these kind of specialized optimizers in the Julia lab and such. But he ended up graduating before we got this far along on the project. So now I'm going to find the next, basically, I'm mentioning it in a few different JuliaCon talks, like, oh, one of the big things we're going to work on in the near future is optimization.jl a lot, right? One of the next MIT students I want to have come in will not be doing ODE methods or nonlinear solve methods, but actually nonlinear optimizer methods. I think first project is, do an IP-opt from scratch so that you can get more performance out of that and boundary value problems. And then other thing is methods for DCP, so being able to take a nonlinear function at the compiler level, prove whether it's whether it's convex or whatnot, right? And then these kind of things to be able to, at a compiler level, change things to sequential quadratic problems and all these extra things. So that whole range of optimizers that kind of can integrate symbolic numerics and compiler tricks, I think is a whole 5-year story for somebody. And I think that's how we'll get that part of the story, because it's already using optimization.jl, so if that piece ever gets into optimization.jl, then it'll just hook together and that algorithm exists. So yeah, I mean, if anyone is out there and wants to if you're joining MIT and you're asking for me what kind of projects are available, I'm probably going to send you this clip, and this is exactly what I'm referring to that is a potential PhD project.
I have a quick question. When doing parameter estimation, how does this scale with the number of parameters?
Yeah, that's a very good question. It scales with the number of parameters in a way that is cubic, right? Because of the LU factorizations involved in it, which is actually the same scaling that you get from an ODE solver that is doing the Gauss adjoint method, right? When you do this with a stiff ODE solver. So is this going to be faster or slower than using the IVP methods? Well, as I mentioned, the shooting methods end up being a lot faster because the nonlinear system that you're solving here ends up just kind of large, right? So whenever the shooting methods end up working, using a shooting method plus an adjoint derivative is just going to be faster, right? But where this is actually kind of interesting, and I have a student that is currently looking into this, is if you do have a parameter estimation problem that's extremely difficult, because of the stability properties of this process, this could actually make it so that way, if it's not fitting using an optimizer, it could actually fit using the boundary value problem solver. And so then one question that you might have is, well, have you tried fitting a neural ODE, where you just put the ODE inside of there, and then the constraints of your boundary value problem is that that your line should go through the data points? The answer is yes. It's about 2 to 3 times. Well, Avik found one case where it was 10 times faster than the normal way we do it. Another student found that there's a 2 to 3 times slower issue. But then what we're also looking at is, okay, for some of these problems that are really difficult to fit with neural ODEs, such as, for example, some of these highly stiff problems that come from chemical reaction theories and such, right? Can this be something that is stable even when other techniques are unstable? That's something that's still kind of in flux. The first thing that people were looking at was the prediction error method things, and then there's a talk that Helmut gave about what happened with the Neuroblocks crew, and they showed that worked for them, right? So it's like, oh, we didn't have to go to this high-powered piece yet. But I think that there's other cases, specifically with what we're doing with Julia Hub and Dyad in terms of some of these very difficult systems for which this might be the method that is best for parameter estimation, but that's still an unproven claim, right? There needs to be some benchmarks on that. I will say one piece about the collocation method. So with the collocation method, because you do everything at all time points at once, it's the everything everywhere all at once kind of approach, the issue is you cannot step to a discontinuity and handle it. So you cannot handle callbacks in this form, and you cannot handle events, and that is one major downside for some applications. So I think that for parameter estimation, this will be a lot better for a lot of these very stiff cases in differential algebraic equations, but it will not handle in the cases with events, which I think is the one downside that I think is inherent to the method.
All right, I think, okay.
Yeah, give Eric a shot.
Very impressive work. Sometimes we do the same problem over and over again, and I'm wondering, is there significant overhead under some scenarios, and is there a way to kind of say, remember this structure so you don't have to recompute quite as much when you do the same problem 100,000 times?
Oh, good point. Well, so the interesting thing about this, okay, so let me show, let me do. So, okay, one of the things with these constraints, right, is you say, okay, let's say I have a constraint where I say x at the point pi over 4 is equal to pi minus pi over 2, right? When you have that constraint, what ends up happening is the sparsity pattern of the green part is the sparsity pattern of your constraint function is dependent on where in the time stepping pi over 4 tends to be, right? So, is it between the second and third time step? Is it between the fourth and fifth time step? This is where the sparsity detection comes from, right? It's like, tell me for the given time stepping setup what the sparsity pattern of this matrix is, and it's dependent on what your current choices of delta t are. So if you make those constant, then you have a constant sparsity pattern, right? But then when you do time stepping adaptivity, right, you might add more points before that, in which case in the array, what used to be like, this is computed by a linear interpolation between the fourth and the fifth time point, now might be a linear interpolation between the eighth and the ninth time point, right? In which case the sparsity pattern changes, and then the optimal way to do an automatic differentiation changes. And so it's hard, what we were able to do is we're able to cache one function for the reverse mode automatic differentiation and cache one function for the forward mode automatic differentiation, and then we use what's known as coloring vectors to be able to call it in a way that is specializing on different sparsity patterns. So it doesn't need to recompile, and it doesn't need to be recompile. It needs, and there really isn't something that you can kind of specialize on there, because every single time that you do the different adaptations and such, you're going to get different, sparsity patterns. And then if you're using different parameters and whatnot, it might specialize it might adapt the time stepping in different ways, and so it kind of makes it hard to be able to say, reuse this specialized matrix solve, because you're going to get different sparse matrices each time when you do this, and that's kind of built into the inherent method, and it's optimized. I don't think that there is much you can cache on that anyways, but it is something to be aware of that is like highly dynamic in terms of the sparsity patterns.
All right, I think that's all the time we had, but let's thank Chris again for the wonderful talk.